I welcome you all to the Spark Research YouTube channel. This is Dr. Vijendra, Assistant Professor in the Department of EC, and here is the another session for this particular course, Analog and Digital Communication. And in this session, we are going to take the contents from fifth unit, that is, and this is the part first. So this is the belongs to the information theory, and here we are going to take the contents particularly from this entropy, the information rate, then the source coding theorem and the Huffman coding. So let's start. So here is the syllabus for your final unit. So basically this is related to the information theory, right? And here in this session particularly we are going to cover all these three topics. The remaining topics we will cover in the another session. So question first is what is this information? So information is nothing like it's a measure of the surprise or the information content. So how will you measure the measure of the surprise? So whenever the chances of that any event is very common, right? Means if it is a very regular, means the information will be very less. Uh, and if suppose the information your event is very rare, means it can happen very rarely, then information will be very high. Means inversely you can say if probability is high, means what? If probability is less, then information is very high, and if probability is high, means information will be very low. So inversely proportional. So directly you can say Ix, that is information, is inversely proportional to the probability of the event. Or you can also write Ix is equal to minus of log of P of X. Or you can also write instead of minus you can write log of and 1 over Px, that is inversely proportional. So both are same only, right? So here this is the equation which with the help of that you can find out the information for any masses or any event. So I will find log of 1 by px or minus of log of px. Okay, so masses, what is this masses? So information is a measure of uncertainty. Uncertainty means which event is rare. The less is the probability of the occurrence of a certain message, the higher is information. So that exactly means if a probability is less, so information will be very high. So inversely proportional. That's exactly we saw. Since the information is closely associated with the uncertainty of the occurrence of the particular symbol, so when the symbol occurs, the information associated with its occurrence is defined as your this equation that we have already seen in the previous slide. So this is the most important equation that you have to remember. So Ik is equal to log of 1 by pk, and that is equal to nothing minus of log pk. K is the event. So where pk is the probability of occurrence of symbol k, and Ik is the information carried by that symbol k, right? Okay, so this is the most general formula in order to find out the information. So here some properties are there. So if isk is equal to 0 for pk is equal to 1, means if probability is very high, not very high, exactly 100%, in that case there is no information, so isk will be 0. And if probability is like suppose in between 0 to 1, of course, then in between information will be greater than equal to 0. So these are the actually the some properties that you can remember. And major thing is for your binary purpose you can calculate like this. Your isk will be log of 2 1 by p of k. Base will be 2 for only binary the events, right? Now what is this entropy? So entropy is nothing, your entropy, that is h of x equal to p of x into log of 2 of p of x. Now actually we are considering for our channel, right? Means binary signals only. So the entropy, for that entropy will be the p of x log of p of x, and here we are using the minus. Otherwise you can write p of x into log of 1 over p of x, and then keep on adding for all the information, then you will get the final entropy. So entropy is nothing the addition of all the information, right? So this will be average actually. So again, the for predictable masses your entropy will be very high, and for low entropy, and for more information, like if it is very rare event, in that case your like less information is there, so that may be the common event. So how we'll find out? So entropy, like here you can see the entropy is an average information content for given source or symbol, right? So this is nothing average information content, right? Information already we have found, and entropy is also defined in terms of the probabilistic behavior of the source of the information. And how will you find out? So h of s you can find that is entropy is equal to k is equal to 0 to k minus 1, the number of the events pk, and log of 2 1 by pk. We will see the some examples, so how to find out the entropy. Entropy is a very important parameter. So remember this line, entropy is an average information content for given source or symbol. One of the important. So here one of the examples, find the entropy for source alphabets, like the events are there and having the probabilities p0, p1 and p2. These are the probabilities. So how will you find? So according to formula, use that formula, hk is equal to k equal to 0 to k minus 1. K is equal to 0 means how many events it have. So here right now see, so total how many events? 3 events, right? 3 source of alphabets are there, so that is why we will use k is equal to 0 to k is equal to 3, then pk and log of 1 by pk. So pk is what? Probabilities. So probabilities are already given. Okay, so let's start. So for first one, that is p0, you can find here like p0 log up to 1 by p. So put the values here. If you'll put the values, then you will get 1 by 4 log of 1 over 1 by 4, that is 1 that will become the 4. Similarly for this again p1, again 1 by 4 and log of 2 4, and this one also you will get, and finally if you'll solve you will get the 3 by 2 bits, right? Okay, so properties, there are the some properties. So building on the definition of entropy, like already we have discussed. So here discrete for random values, your h of s, that is entropy, will be in the range of the 0 to log of 2 of k. So this is the range of the values of your entropy. And so here the h of s will be 0 only if the probability pk is equal to 0, and h of s equal to log of k if and only if pk is equal to 1 by k. And so here upper bound on entropy corresponds to maximum uncertainty, that is d of p by q equal to k is equal to 0 to k minus 1, and pk already we have discussed log to pk by q. Okay, so here is the graph of the function of x minus 1 and the log of x versus x. So how the probabilities, the will fall in this range only. So that exactly it is showing. Okay, so rate of information. Now another topic is here. So rate of information, that is R. It will tell the entropy multiplication of the entropy and the event, how many times it will occur. So entropy bits per symbol, and rate and the symbol rate will be the how many bits or how many symbols per second you are sending, the speed of the symbol, that is frequency, symbol per second. So that is how you can find out the rate of information. So rate of information is if a source generates at a rate of r messages per second, the rate of information r is defined as the average number of bits information per second. So h is the average number of bits per second, and how will you find? R is equal to r into h. Okay, so finally we are moving to the source coding, that is the important topics, and whatever we have discussed till now, that is the just the background. so that we can talk about the source coding. So source coding is the process of compressing data into a smaller form of the efficient transmission and storage. So for both purpose it will be used source coding, not only for compress the data, but also like whenever you are sending the information, if the data is compressed into the low number of data, it will be very easy, right? And you can also store it at the same time. Okay, so source coding techniques, so we are going to take the some examples related to the source coding technique, but here is the representation of data generated by discrete source of information. The process by which the representation is accomplished is called the source coding, right? So discrete memoryless source is there, then the source encoder, and then finally binary sequence that we are going to send. And the source encoder, we have the different types of the techniques. So as for example, we can have the Huffman and Shannon-Fano, so we will look into that. And for that we can find out the efficiency for different source coding technique. The efficiency, we can find the eta is equal to h of that, that is entropy, already we have discussed how to find. And that is the, the code word length, that is the how many bits we are going to use to encode that particular information. So here is some more detail about the your code word. So here L, that is code word length, you can use this equation pk into ik, and efficiency is the ratio. Here the efficiency, coding efficiency of the source encoder is L minimum divided by L dash, and L minimum is nothing, your h of s, right? So here like L minimum is h of s, so that equation if you replace, you will get eta is equal to h of s by L. So let's see the one example. Huffman is the one of the example of the source coding technique. So with Huffman code, in the binary case, the two least probable source output symbols are joined together, resulting in a new message alphabet for one symbol. As for example, application is JPEG, MPEG or MP3. Advantage, it can be uniquely decodable code, and of course the average code length will be comparatively lesser. Disadvantage is that large table gives the some little bit complexity. And how will assign any code like Huffman code for any message, so we will look into that. So here are the some steps that you should remember. So create a list for the symbol in decreasing order of the probability, right? So this is the step one. Arrange it in a decreasing order of the probability. Then symbols with the lowest probabilities are assigned as 0 and 1. Okay, the next step is that these two symbols are combined which have the lower probability to a new symbol with the probability equal to the sum of their individual probabilities. The new symbol is placed in the list of its probability value. So means we'll keep on arranging the in the decreasing order, right? So the step second, the next step is that the procedure is repeated. We'll keep on replacing until it will reach to the top, right? So we left with the once we left with the only two symbols, means further we cannot the arrange in the decreasing order. Till that we will keep on. So bubbles type, right? Huffman code is bit sequence obtained by the working backward tracking sequence of 0 and 1 assigned to that symbol and its successors. Okay, so we'll look into the example so that we can understand it in a better manner. So here is the Huffman coding. Suppose these are the source symbol as 0 to S4, and here is the probability. So probability, if we'll see here, its random values are 0, right? 0 0.1, 0 0.2, 0 0.4, 0 0.2, 0 0.1. So step 1, what are we going to do? First of all, we will arrange these probabilities in the decreasing order. Means on the top, what are we going to do? On the top, we will keep this 0.4 on the top, right? And then 0.2, and then further this 0.1 will be come back to here, right? So we'll arrange in that manner. So here now see, top one have the highest probability. Now the 0.2, 0.2 and the 0.1 and 0.1. So all these probabilities now arranged in a decreasing order. So step 1 over, and correspondingly you can assign the symbol, right? Then step second, now add the lowest two probabilities. So if you will add, what will happen? You will get 0.1 plus 0.1 equal to 0.2. And after adding, now again arrange in the decreasing order. So 0.4 is higher than 0.2, means the summation, so it will be on top. Then 0.2, like here all three are same, but we will give the highest priority to our values. So directly we will bring it here 0.2, and that this 0.2 will be shifted here, this 0.2 will be shifted here, means just go down. And now next step, again we will keep on adding, right? So again if you'll add 0.2 0.2, then now how much we'll get? 0.4. So the 0.4 have the highest values, means this is equal, but again our results will have the highest priority, so 0.4, and this 0.4 will be shifted here, and 0.2 is going, will continue. So again now we will get the addition 0.6, right? So here now see 0.6 is greater than 0.4, so we will keep 0.6 and 0.4 like that. Okay, now after that we will assign the values. So values are 0 1 0 1 0 1 and 0 1. After assigning these values, now finally we will write the bit pattern, that is Huffman bit pattern for these symbols. So how to write, let's see here. So first we will move like from S, like from left to right, and we will write code from right to left, right? So just reverse. So as for example, S to see here, is there anything? Nothing, 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 nothing. Here we will go down, then 0, okay? 0 we will keep, and then what to do here again, then we will follow this track, this track, this track, this track, okay? 0, okay? So we found 2 0. So this is your first 0 and this is the second 0. So we got the 0 0 code for first S2 bit. Similarly for another bit S1, we will move from left to right, and data we will move from right to left. Okay. So S1 nothing, the thing go back. Here we got 0, right? Here we got 0. Then again move up. We are going move up, then go down down here, and we are getting 1. So 0 and 1 we got. So here first bit is 0 and second is 1. So left to right. So we got 1 0 code. Similarly for S3, now if we'll check, this is your, what are the values? Here 1 values, and then go up 1, and then here again 1. So here the values are 1 1. Similarly for S4, you will get 1, and then move from here 1, and then move from here 0. So 1 1 0, like that you can get. So this is the final patterns of the Huffman code for these probabilities, like these informations that you want to transmit. So this is the technique, right? So here is the, now finally you can find out the code word length. So here code word length is probabilities and into the how many bits that you are going to use to transmit that particular message. So add all those, you will get the probability, the code word length. And then entropy you can find for all the message. So probability into log of 2 1 divided by probability. You put all these values, you will get the bits. Finally efficiency you can find entropy divided by elders. Okay, so here is the another example. Suppose L dash you can find very easily, that is probability into code word length. So here code word length is actually is for S0. Suppose here how many code word length we are going to use? 2. So here 0 point, and what is the probability of this message? So 0.4. So 0.4 into 2 plus again for this S1 0.2, and here 0.2, and code word length is 2. So 0.2 into 2 for S3, again probability is 0.2 and code word length is 2. So 0.2 into 2. Here probability is 0.1 and the code word length is 3. So 0.1 into 3. For last one also the code word length is 3 and probability 1. So 0.1 into 3. So in that manner you can get the total values of the code word length, that is L. Next step is to get the entropy. So here if we will repeat the same steps, you will get the code word length and these steps. So probability is given, and probability, so like that probability is 0.4 and log of 1 by 0.4, right? and 0 for as one message, that is probability is given 0.2. So 0.2 into log of 1 by 0.2, and keep on adding for all these probabilities, you will get this one, right? Further, you can find the efficiency also. That's all in this session. Thank you to join. If you have any doubts, please drop your comments.